We are from the University of Southern California, and I am going to be presenting our paper titled ABLATOR, Robust Horizontal Scaling of Machine Learning Ablation Experiments. Ablation experiments are increasingly important in examining the effect an architectural component has on a model. For example, from the figure, we ablate the architecture of a transformer model to find the importance of multi-headed attention, layer normalization, and more. Their unique combination can have additional interaction effects that require us removing both components. The result is an exponentially increasing search space with respect to the increasing model complexity. Current frameworks focus on scaling the training of a single large model, while there are few frameworks that focus on horizontal scaling of multiple models on a multi-node cloud environment. There are several issues that can arise when scaling an experiment horizontally. First, manual resource allocation can be error-prone. Number of GPUs, memory available on each node can differ. It is not as easy as to distribute the model across all nodes and specify a device to run. Second, when a single experimental trial encounters an error, it can often cause the entire node to fail. While the error trial could have been a result of a temporary error, such as unavailable resources. In such cases, rescheduling the trial can fix the same error. Managing experiment results is also error-prone, where a user has to copy the individual results from several nodes to a centralized location. Nodes are often ephemeral, such as Docker containers, and it is frequent to lose experimental results. All of the aforementioned errors can then propagate to the analysis and have us incorrectly conclude that a trial performs better than it should. While manually analyzing several results and combining them is cumbersome. ABLATOR is our open-source project that can automate the horizontal scaling of several experimental trials. It is designed to work on a local environment for fast prototyping and with the ability to scale to a cloud environment. The same code can run both on a local machine and a multi-node cluster. ABLATOR automatically scales experiments, manages the execution and consolidation of all artifacts. Additionally, ABLATOR is designed with state persistence in mind, where sufficient information is stored for a trial to restore its state. Next, it is fault-tolerant, where a single failed trial is not catastrophic. And last, the analysis is automated, as well as a lot of boilerplate code is removed for training and checkpointing a model that improve the speed at which a user can prototype. The figure depicts the architecture of ABLATOR and compared to performing the same experiment manually. When performing the experiment manually, the user would have to combine several libraries and manually configure them to work together. Errors in earlier stages of the experiment lead to erroneous analysis. ABLATOR is built using the RayCore library and manages the execution of the same experiment end-to-end. All the user has to provide is the code of a method and a configuration file, while ABLATOR manages the execution and produces analysis results. We identify several errors that lead to difficulty in scaling experiments horizontally that are specific to machine learning. As the training is stochastic, to describe its state it requires to maintain the initial and present experiment conditions. The initial conditions can be stored via the configuration file, while the current experiment state is stored on the model weights, training statistics, and more. Last, the outcome of the training can be described by the analysis artifacts as the final state. The introduced stateful experiment design allow us to robustly restore the state of an experiment. We design a configuration system specific for multi-node systems, where configuration attributes can change between nodes or execution runs. For example, the experiment directory will be annotated as stateless. Specific to machine learning research is defining configuration attributes that are derived during execution. For example, the output size of a neural network can be based on the dataset definition, like the number of classes in the dataset. Last, the Pythonic definition of the same configuration allows us to avoid errors due to misconfigured experiments and the dynamic inference of the configuration. Based on our meta-analysis and previous works, misconfigured experiments lead to the most errors during experimentation. For example, it is easy for a practitioner to incorrectly store or load a configuration, leading to the use of incorrect values during execution. Managing a large number of configurations through a command line interface is cumbersome. Important to Ablator is the automated analysis. The information stored on the cloud allows us to evaluate the progress of the experiment at any stage. The automated analysis allows us to abort an experiment or start another experiment informed by the results of the currently pending experiment. For example, a practitioner might conclude that ATOM is the best performing optimizer for a method. As such, we can avoid ablating the performance of the same method using other optimizers. We perform a case study where we empirically evaluate Ablator. We study how different data preprocessing methods, model architectural components, and training hyperparameters affect the performance of a transformer model applied on tabular datasets. We name our model Tablator. We run the largest to-date ablation study where we evaluate 2,337 trials. We present a sample of our case study in the next slides while the full results are accessible in our paper. We demonstrate the kind of insights a user can obtain from using our tool for attributes that take numerical values. For our particular case study, we conclude that increasing the number of layers for this particular model can lead to higher performance variance but improved performance. The higher performance variance is not always acceptable, such as for methods that have to be continuously trained. As such, Ablator artifacts provide a holistic view of the model's performance while the interpretation requires user input. We demonstrate the artifacts that a user is able to obtain for categorical attributes. For our case study, we also ablate the importance of an optimizer on the model's performance. We find that different datasets have different optimizers perform the best. Our results suggest the need for ablation experiments specific to the dataset. In detail, we find that ATOM performs the best for one dataset, but not another. As models get larger, the number of ablating components increases. Additionally, there are several interaction effects between the presence or absence of individual components. When developing a method and evaluating a new idea, it is necessary to fully understand how it interacts with other components. Ablation experiments evaluate whether it provides an improvement or degrades the model's overall performance. Next, we find that there is no single method that works best for all datasets, and several experimental trials are required to find what works best. The large scale of these experiments make them labor-intensive, and automation is required, both for the execution as well as the analysis of the results. We have additional analysis on things that can go wrong when horizontally scaling experiments in our paper, as well as additional insights from our case study on what worked best for our tabular transformer model. If you would like to get involved, our open source project is in active development and early beta version. You can visit our project page by scanning the QR code. You can star the project to stay up to date with our releases and show your support. We welcome contributions and feedback.